Alright, so this is our AP Chemistry Chapter 5 lesson video, Part 5, and I'm going to cover Section 5.7. And so again, this is a math-intensive section, so I'm not going to lie, the video will probably be incredibly long. So we'll do the best we can to get through it. So we're going to talk about enthalpies of formation. So the enthalpy of formation, which is represented by delta H sub F, the F just stands for formation, is the heat change that occurs with the formation of a substance from its elements. The standard enthalpy change, which is delta H with a little, looks like a little degree sign, that always means standard, is the heat change that occurs with all reactants and products at their standard states at 1 atm and 25 degrees Celsius. So that's important. We need them at their standard state. So for example, oxygen's standard state at 25 degrees Celsius and 1 atmosphere pressure is O2 gas. It's not O2 liquid. So that's important right there. The standard enthalpy of formation, or delta H formation with the little degree sign for standard, of an element in its standard state is 0 kilojoules per mole. So elements in their standard state have a 0 standard enthalpy of formation. So you can find the enthalpies of formation in a table in your book. So those will be provided to you. So on the AP exam, obviously, you won't have your textbook. So they'll let you know the numbers that you need to know. But you're going to see me pull a lot of numbers in this section. That's where I'm pulling them from, is the standard heat of formation table in your textbook. So which of the following reactions at 25 degrees Celsius with the enthalpy change represent a standard enthalpy of formation? For each that does not, what changes are needed to make the equation whose delta H is an enthalpy of formation? Alright, so I just need to make sure that I am starting with elements in their standard states to make something. Alright, so sodium is naturally a solid, oxygen is naturally O2 gas, and it's going to form sodium oxide solid. That one is. So that would be a standard enthalpy of formation. Here we have potassium as a liquid. Potassium is a metal. It is not naturally a liquid. The only naturally liquid metal is mercury. So this would not be a standard heat of formation. So how can we fix it? Well, we would need potassium to be a solid. However, Cl2 gas, that is accurate, making potassium chloride solid, that's fine. So really the only thing that would need to be changed about part B is potassium would need to be a solid. Alright, part C, we're starting with a compound. Remember, for standard heat of formation, we need elements making a compound. So for part C, this would not be a standard heat of formation because I would need to flip the reaction. Alright, I need the carbon, the hydrogen, and the oxygen on the reactant side going to make the glucose. Alright, so H2 is normally a gas, O2 is normally a gas. The only other thing that you would probably want to change is carbon normally is in graphite form. Okay, so that might be something else you would want to change about this one, but you would definitely need to flip the reaction to get that one to be a standard enthalpy reaction. Alright, so like I said, states of matter are very important. They're also important for the numbers you're going to see me pull. Like if you think I'm pulling the wrong number, check the state of matter. Alright, so it says, write the equation corresponding to the standard enthalpy of formation of liquid carbon tetrachloride. So remember, this needs to be my product. So we have liquid carbon tetrachloride, so that's a liquid. That's going to be my product. Alright, so I need to start with my elements. So we're going to start with carbon, like we said, normally it's in its graphite form. And then what is chlorine when it's by itself is Cl2, and it's a gas. Alright, however, we need to balance this thing. So we have 4 chlorine, so I need a 2 right here, so that way it can be balanced. Alright, so again, standard heat of formation just deals with forming a compound from its element its elements in their standard states. Alright, so a lot of times we want to look at a reaction and find the delta H of the reaction, and we can do that using the standard heats of formation. But it is products minus reactants. Okay, so it's your delta H or your standard heats of formations of the products minus the reactants. A lot of you want to do it backwards. Remember, a lot of our deltas are always final minus initial. So you end with products, you start with reactants. Okay, so best thing to do is just jump right into one of these. Alright. Oh gosh, this is super long one. Oh my gosh, there's a couple of ones when I was pre-looking at what I was about to cover, and this is one that's very long. So it says, calculate the standard enthalpy change for the combustion of 1 mole of benzene, which is C6H6 liquid, to form CO2 gas and H2O liquid. Okay, so notice they're giving me the states of matter. That's because those are important for when we're picking the delta H from our table. All right, so we're combusting our C6H6 liquid. And so remember, in a combustion reaction, that's when something burns in the presence of oxygen. Okay, so see, you have to remember these things, like all of it's connected. And then it's going to form carbon dioxide gas and water in its liquid form. Okay, which again is important. Water in the liquid form and water in the gas form have 2 different delta H's on your table. Alright, so before we use a reaction, you know you always need to balance it. Okay, so it says for the combustion of 1 mole of benzene, that becomes important. That means this number needs to be set at a 1. So you know how sometimes we have to like double reactions and things like that? That means I don't want to do that this time. If so, you can, but you'll just need to adjust your answer at the end. Alright, so I have 6 carbons here, so I need a 6 here. I have 6 hydrogens, so I need a 3 here. I have 2 oxygens here. I have 12 plus 3, which is 15. So this would, in other words, be 15 halves. Or you could do 7.5. Either one works. Normally, then we would go back and double everybody to get rid of that half. But we only want it for 1 mole of benzene. So I'm just going to leave it as the 15 halves. And that's okay for this problem. All right. So remember, we know our delta H. You'll see me write it like this for shorthand in class. It's just the products minus the reactants. So let's look up all our numbers. Okay, so for C6H6, it is 49 kilojoules per mole. Okay, I pulled that from the table. Oxygen, O2 gas, is a naturally occurring element, so it's 0 kilojoules per mole. And see, a lot of times that's what throws you off, is you'll be like, wait a minute, I don't see this one in the problem, because you're expected to know if it's an element in its natural state is 0. Carbon dioxide gas, this is negative 393.5 kilojoules per mole. And then water as a liquid. Okay, remember, you're going to have a number for it as a liquid and a gas. It's negative 285.8 kilojoules per mole. Okay, so I pulled all of these numbers from the chart. The problem is, though, these are all kilojoules per mole. I don't necessarily have 1 mole of everything, so I do need to take into account the coefficient. So this one, I really do just have 1 mole, so it will stay as 49 kilojoules per mole. 0 times 15 halves is just still 0. Negative 393.5, I have 6 moles of that, so I need to multiply this number by 6. So that becomes negative 2,361 kilojoules per mole. And then this one, I have 3 moles, so I need to multiply it by 3. It becomes negative 857.4. Oh, 4 kilojoules. Alright, oops, sorry, I forgot to drop my per mole for each of these. Sorry about that. Because we multiplied by how many moles we had. So now it's just kilojoules. Alright, so now we're ready to plug in. Now just to let you know, I'm not going to write all of this out every single time. Okay, this is just me showing you. These are the original numbers from the chart. These are where I multiplied them by their coefficients. Alright, from now on, I'll just write where I've already multiplied them. So now we need to do products minus reactants. So I start with my products. So I have negative 2,361 kilojoules plus a negative, so I'm just going to put minus, 857.4 kilojoules. Okay, so that's important to note that I'm actually adding these two. It just happens to be a negative. All right, and then we subtract our reactants. So we have 49 kilojoules, technically plus 0 kilojoules. Obviously, normally you would just leave off the 0. Okay, I'm just trying to show you where I'm getting everything for the first time. All right, so I end up getting negative 3,267.4 kilojoules, just like that. Okay, so again, all I did was find my numbers off the chart, multiplied them all by the coefficients, did products minus reactants. That was it. Okay, So this is where it gets super long, if you didn't already think this was long. So it says, compare the quantity of heat produced by the combustion of 1 gram of propane to that produced by 1 gram of benzene. So that means I need to do this process for propane now, because they didn't give me the delta H for propane. That would be convenient if they did, but they did not. All right, so propane is just C3H8. All right, propane is also a liquid. It's combusting, so it's going to burn in the presence of oxygen gas, and it's going to make CO2 gas and H2O liquid. All right, so first thing I need to balance this thing. Remember, we're trying to get it about propane, so I want to keep propane with a coefficient of 1. So carbon I have 3, so I'll put a 3 here. Hydrogen I have 8, so I'll put a 4 here. Oxygen I have 2. Here I have 6 plus 4, which is 10, so I'll put a 5. So I'm keeping my 1 with propane, which is perfect. All right, so like I said, I'm not going to write the original numbers. I'm just going to go ahead and write the numbers that I've multiplied by the coefficients. So for propane, it has a coefficient of 1, so the number remains the same. It's negative 103.85 kilojoules. So remember, I've dropped the per mole because I've multiplied by the fact that I had 1 mole. All right, oxygen is 0, but I'm going to multiply that by 5 moles, so it's 0 kilojoules. Carbon dioxide gas is negative 393.5 kilojoules per mole, but I'm going to multiply by 3 this time. So I end up getting negative 1,180.5 kilojoules. And then liquid water is negative 285.8 kilojoules per mole, but I'm going to multiply it by 4 this time. So I get negative 1,143.2 kilojoules. All right, so once I have those, I'm ready to do my products minus reactants. So my delta H is my products. So I have the negative 1,180.5 kilojoules plus my, well, here I'll just change it to a subtraction because it's minus my 1,143.2 kilojoules, and then minus my reactants. So I have negative 103.85 kilojoules plus my 0 kilojoules. And like I said, most of y'all, you'll probably just leave off the 0. So for this, I get negative 2,219.8 kilojoules. See, the unfortunate thing is, at this point, you probably think, oh, well, good, I compared the two numbers. Boy, that was a long problem. But we did not yet, because we need to compare it per 1 gram of propane. Okay, so see, this is per 1 mole of benzene. This is per 1 mole of propane. Okay, so I got to get from grams to moles, so then I can get to my heat. All right. So let's just do, I did propane first, it doesn't matter. So I did 1 gram of my propane, which is my C3H8. So first thing I need to get to moles. So I use my molar mass, which for propane is about 44 grams. All right, and then I know for propane, this is how many kilojoules I get per 1 mole of propane. I know it's per 1 mole of propane because propane has a coefficient of 1. All right, so negative 2,219.8 kilojoules per 1 mole of propane. So my grams and moles cancel, and so I got negative 50.45 kilojoules. Okay, and so this is what happens for propane. But we have to compare it to our benzene. So I grab my 1 gram of benzene, which is C6H6. I do the same thing, I need to get it to moles. My molar mass for benzene is about 78 grams. And then for this number, I know it's for 1 mole of benzene because it has a coefficient of 1. So I do negative 3,267.4 kilojoules per 1 mole of benzene. So my grams and mole cancel. Once I multiply and divide, I get negative 41.89 kilojoules. This is for benzene. So, whew, goodness, now I have compared the quantity of heat produced from 1 gram of propane to that for 1 gram of benzene. So in other words, propane is going to release more heat per gram than benzene will. My gosh, that was a long one. All right, I'm just hoping this video isn't going to end up being an hour at this point. I feel like it's already been an hour. I'm not going to lie, I don't mind doing standard heat of formation problems, but teaching it is kind of dry. It's not my favorite topic to teach. All right, so moving on to hopefully something shorter. So it says, use the standard enthalpies of formation listed in table 5.3. So it's table 5.3 in the book that I was using, but in your textbook it may be different, and we got a new edition since I made this PowerPoint. So it could not be table 5.3 anymore. Calculate the enthalpy change for the combustion of 1 mole of ethanol. Alright, so we have our reaction right here. So yay, this one will be shorter. So I just looked up my numbers. So I find my number for my ethanol, and I only have 1 mole, so it ends up being negative 277.7 kilojoules. For oxygen, it is an element in its normal form, is 0. 0 times 3 is still 0 kilojoules. Carbon dioxide gas is negative 393.5, but I'm going to multiply that by 2, so it's negative 787 kilojoules. And liquid water is negative 285.8, but I'm going to multiply that by 3. So it's negative 857.4 kilojoules. And so then I just do, of course, delta H is products minus reactants. So I just plug in. So my products are negative 787 kilojoules plus my negative 857.4 kilojoules minus my reactants, which is negative 277.7. Oh gosh, what happened with that 7? 7 kilojoules plus 0 kilojoules. And so then I end up with negative 1,366.7 kilojoules. Okay, so y'all, important thing is, this is obviously not very hard, but because there are so many negatives, a lot of you actually just play it into the calculator wrong. So that's the main thing you need to practice, is just getting the correct answer. Okay, it's not the setting it up that's hard, it's just there's lots of negatives, and there's sometimes where you need parentheses and things like that. So just make sure you can get it into the calculator correctly. Alright, so what we focused on so far is if they give me the reaction, I use the delta H's to get the delta H of the reaction as a whole. But sometimes what they'll do is they'll give you the delta H of the reaction, and they'll have you find one of the standard heats of formation that is not in the table. Okay, so that's what's happening here. So here's our reaction. It says standard enthalpy change is 178.1 kilojoules. So you can just think of it as this right here. So it gave me the delta H. From the values for the standard enthalpies of formation of calcium oxide and carbon dioxide gas, given in table 5.3, calculate the standard enthalpy of formation of calcium carbonate. Okay, so in other words, we know these two, we're looking for this one. Alright, so let's go ahead and write what we know. So for CaO, when I look on the table, it's negative 635.5, and there's only 1 mole, so it's negative 635.5 kilojoules. For carbon dioxide, it's negative 393.5, and since there's only 1 mole, it's negative 393.5 kilojoules, and this is what we don't know, so I'm going to put an X. Okay, so we know delta H is products minus reactants, but this time we actually know delta H. So delta H is 178.1 kilojoules, and that equals my products, so negative 635.5 kilojoules plus a negative 393.5 kilojoules minus my reactant, which is X. Okay, so now all I need to do is solve for X, which again, in and of itself sounds pretty simple, but a lot of you might mess up the math. Like you might forget it's minus in X, so X is technically negative right now. You might have forgotten this negative sign. There's just so many things that you could do wrong. But once you solve for X, you should end up getting negative 1,207.1 kilojoules. Okay, so see, if you're struggling to get from this point to this point, that's something you need to ask me in tutoring. Okay, because I can go over how to solve for X in tutoring, but that's a skill you should already have before you enter my class. Alright, so hopefully that wasn't that big of a deal. So let's look at another one. So don't forget to be trying some of these on your own now. Alright, so you try this one, pause it, and I'll assume you've done that. So it gives us this reaction, here's our delta H, and it's asking us for the standard enthalpy of formation of CuO. So let's plug in what we know. So we don't know CuO, so I'm going to put an X there. Hydrogen gas is a natural element, so it's going to be 0. It's only 1 mole, so 0 kilojoules. Copper as a solid is a natural element. It's going to be 1 mole, so 0 kilojoules. Water as a liquid, let's see, whoops, where's my water? Negative 285.8 kilojoules, it is 1 mole, so it'll stay negative 285.8 kilojoules. And so now we're ready to solve. So remember, we know delta H is products minus reactants. But this time I know delta H. It's negative 129.7 kilojoules. And it's my products, which is 0 kilojoules, plus a negative 285.8 kilojoules, minus my reactants, which is X plus 0 kilojoules. And so again, you can just get rid of the 0 kilojoules if you want to. That's fine. Just don't forget that right now X technically has a negative in front of it for when you're solving. All right, and so once we solve for X in this case, you should get negative 156.1 kilojoules. So hopefully you got that one right. And so again, if you're struggling to solve for X, that's something you need to come to tutoring for. Because again, that's a math skill that you should already have before you enter this class. Being able to solve for X, I mean, that's basic math right there. Basic algebra. All right, we are nearing the end. To the very long sample integrative exercise. So it says, trinitroglycerin, which is C3H5N3O9, usually referred to simply as nitroglycerin, has been widely used as an explosive. Alfred Nobel used it to make dynamite in 1866. Rather surprisingly, it's also used as a medication to relieve angina, which is chest pains resulting from partially blocked arteries to the heart, by dilating the blood vessels. So in other words, what they're telling us is nitroglycerin is used to make dynamite, but we also use it to treat chest pains. The enthalpy of decomposition at 1 atm pressure of trinitroglycerin to form nitrogen gas, carbon dioxide gas, liquid water, and oxygen gas at 25 degrees Celsius is negative 1,541.4 kilojoules per mole. All right, so they told us some stuff about nitroglycerin, trinitroglycerin. So let's see what the questions are. So I may have to click back to this slide. All right, so it says, write the balanced chemical equation for the decomposition of trinitroglycerin. Okay, so they told me what trinitroglycerin is, and they told me down here what it forms. Nitrogen gas, carbon dioxide gas, liquid water, and oxygen gas. Okay, so they told me all of that stuff, so I should be able to easily write a balanced equation. All right, so we start with what they told me trinitroglycerin is. So C3H5N3O9 liquid. Okay, they told me we make nitrogen gas. They told me we make carbon dioxide gas. They told me we make liquid water. And they told me we make oxygen gas. Ooh, goodness. All right, so a lot of stuff going on here. All right, so it says write the balanced chemical equation. So now all we have to do is balance it. However, this one, there's probably going to be a few tricks in balancing it. So just make sure you remember our rule. When things aren't working and I have odd on one side, even on the other side, we can just start doubling things. All right, so I have 3 C's. So here I'll want a 3. I have 5 H's. Here I have 2 H's. So I'm already having trouble with an odd and even thing. So what I'm going to do is I'm going to double this. So that way this will be even, but that means I've doubled C. So that means I really need a 6 right here. Not a big deal, okay? So now I have 6 carbons. Now I have 10 hydrogens. So I can easily put a 5 right here. Okay, see, it's all about making it easier for you. All right, next, I have 6 nitrogens, and I have 2 right here, so I need 3. And so the last thing is, what goes here? That's all I need to know. This is where it gets a little tricky. So if you look over here, I have 18 oxygens. Here I have 12 plus 5 plus 2, which is 19 oxygens. Of course. Okay, so whenever we have odd and even, like I said, I always just recommend starting to double things. Okay, now we've already balanced everything else. So let me just double everything. So remember, we don't know what goes here, so I'm not going to do anything with that blank yet. So let's change this to a 4, this to a 6, this to a 12, and this to a 10. All right, so we've doubled everything, so hopefully we can get rid of that whole odd even thing. All right, so now let's look at oxygen. So I have 36 oxygens here. I have 24 here, plus 10, plus 2, which is 36. So I actually don't need anything right there. Okay, so y'all, the whole odd, even, and the doubling thing is super helpful for a lot of reactions, especially ones that are tricky to balance. All right, So hopefully that part wasn't that bad for you. So then part B says, calculate the standard heat of formation of the trinitroglycerin. Okay, so they gave me the delta H, I believe, in the original question, right here. Okay, so it's negative 1541.4. So we'll just put that right here. Sorry, I already forgot what I said. Negative 1541.4 kilojoules per mole. All right, so let's plug in, oh, I don't want to put it right there. I need to write numbers under this. We'll put it down here. All right, so we don't know the standard heat of formation of my trinitroglycerin, so I'm going to put an X for that. Nitrogen gas is naturally occurring, so it's 0 kilojoules per mole. 0 times 6 is, of course, 0 kilojoules. Carbon dioxide gas is negative 393.5, but I'm going to multiply that by 12. So I get negative 4,722 kilojoules. Liquid water is negative 285.8, but I'm going to multiply that by 10. So I get negative 2858 kilojoules. And then, of course, oxygen gas is its natural state, so it's 0 kilojoules. All right, so we know that delta H is products minus reactants. So we know delta H this time is negative 1541.4 kilojoules. And so we do our products, so 0 kilojoules plus a negative 4,722 kilojoules plus a negative 2,858 kilojoules plus 0 kilojoules minus our reactants, which is X. Okay, so don't forget that negative on the X. So all we're going to do here is we are going to solve for X. So hang on, where did I solve for X here? Oh, okay, I went ahead and did that step first. All right, hang on, I'm going to change it up real quick. Remember how I always tell you there's 2 ways to do math. I didn't do it the way I'm showing you right now. I did it the backwards way that I was going to tell you you could have done it. So notice this is kilojoules per mole. That's per mole of the trinitroglycerin. But if you notice, we don't have 1 mole of it, we have 4 moles of it. So see, what I was going to do was go ahead and solve for delta H and then take into account the 4. But when I pre-worked it out, I took into account the 4 first. So I don't want you to have to wait for me to use a calculator. So let me go ahead and address that first. So since this is per mole, what I went ahead and did first was I did negative 1,541.4 kilojoules per mole, and I multiplied that by the fact that I had 4 moles of the trinitroglycerin. Okay, sorry, this is a multiplying by a negative. So when I did that, I got negative 6,165.6 kilojoules. Okay, so like I said, I just went ahead and took into account the 4 moles before I plugged in instead of after, which is fine. Either way works. So let me change this now. That's the only downfall of pre-working it out is then if I decide to go a different route when I'm actually doing it in the video, then I don't have the answers to that. All right, so now when I solve for X, I end up getting negative 1,414.4 kilojoules, and remember that is for 4 moles though, okay, because we've already taken into account the 4 moles. So then I take that number and divide it by my 4 moles. And so I end up getting negative 353.6 kilojoules per mole. All right, and so that's all you got to do for that, okay? And actually you can not even, like I took into account the 4 moles, but if you notice, then I had to kind of take into account for it, so you could skip that portion if you wanted to. It doesn't really make any difference. All right, so let's move on to part C. Hopefully I didn't need any of this stuff for part C, but we'll see in just a minute. All right, so it says a standard dose of trinitroglycerin for the relief of angina is 0.6 milligrams. If the sample is eventually oxidized in the body, not explosively though, to nitrogen gas, carbon dioxide gas, and liquid water, what is the number of calories released? Okay, so we just calculated our delta H, so we are going to need that from our previous one, but I'll just rewrite it when we get to it. So the point is, though, we're starting with 0.6 milligrams. So So obviously we're not using milligrams, and the delta H we just calculated was per mole. So first let's get out of milligrams. So 1 gram is 1,000 milligrams. And then of course we know the delta H in kilojoules per mole, so the next thing is we need to get to moles. So the molar mass of the trinitroglycerin is 227 grams. Alright, so all I've done so far is just go from milligrams to grams to moles, because that's what we're trying to get to. Now I can use the delta H that we calculated. Oh no, we don't even need the one we calculated. They gave us the delta H at the very beginning. So it's negative 1,541.4 kilojoules per mole. Okay, so that's what they gave us at the very beginning. But then it wants calories. So I need to get from kilojoules to joules. So 1 kilojoule is 1,000 joules. And then 1 calorie is 4.184 joules. Okay, so this is just a long conversion problem. Super long conversion problem. So I end up getting negative 0.97 calories. So in other words, 0.97 calories is released when your body oxidizes this low dose of trinitroglycerin. Alright, so let's move on. There's still a part D and E, if you can even imagine. Oh, whoops, I just realized I didn't ever make it to calories in my answer right here, so I need to fix that. And then right here is positive because it asked about it being released, but I should have typed released on there, so I need to go back and fix that. Good thing I noticed that. Alright, so part D, it says one common form of trinitroglycerin melts at about 3 degrees Celsius. From this information and the formula of the substance, would you expect it to be a molecular or ionic compound? Well, we would expect it to be molecular for 2 reasons. One, it has a low, what did it say, melting point? Yeah, melts at 3. So it has a low melting point. We know that molecular compounds have low melting points. But 2, it's made of only nonmetals. Okay? It's made of only nonmetals. I mean, it's C3H5N3O9. So it's carbon, hydrogen, nitrogen, and oxygen. Those are all nonmetals. So those are 2 reasons we would assume it's molecular and not ionic. Ionic tend to have high melting points and are a metal and a nonmetal. Alright, so last one, part E. It says describe the various conversions of forms of energy when trinitroglycerin is used as an explosive to break rock faces in highway construction. Oh my gosh, mine is super long. So I'm going to try, I'll say the long version of it, but I'll just write a short version. So I started with the chemical potential energy. So that's what's stored in the bonds of the trinitroglycerin. Okay? So it's going to explode, which means heat is released. So I put it turns into heat. Also, because it makes a lot of gases, there's going to be expanding, which means work is going to be done on the rock face to break it apart. We'll put expanding next to it. Alright, then once the rock breaks apart, the rock goes from not moving to moving, like it's going to blow up. So that is potential energy to kinetic energy. But then eventually that rock is going to fall back down and rest on the ground. So then we have kinetic energy going back into potential energy. When it hits the ground, it is going to produce some heat through friction. So those are kind of the energy changes that I thought of when I thought my way through that. All right, whew, that was a lot of math in this chapter. My gosh, I am tired now after doing these today. So hopefully though you can wrap your mind around it. It's not that big of a deal. So remember, standard heat of formation, you'll use the ones from the table. You're usually either solving for the delta H of the reaction by doing products minus reactants, or they may give you the delta H of the reaction and you're solving for one of the reactants or products by solving for X.